Hello, everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Timofey Golubev. Timofey is a research scientist at Thermal Analytics, where he works on the development of both physics-based and data-driven models for multi-physics phenomena. His focus areas include thermal-electrical modeling, the photovoltaics and batteries, conjugate heat and moisture transfer, and human thermal modeling. Timofey received his PhD in physics from Michigan State University with his doctoral research focused on photovoltaic modeling and has been a part of the TAI family since 2019. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar and we'll be sending you the link following this presentation. And with that, Timofey, if you're ready, you may begin.
Okay, welcome everyone. Today's presentation is on analyzing the impact of onboard photovoltaics on electric vehicle energy consumption. And an outline is, I'll first introduce the topic, then I will describe the methods for the three main components of the modeling in this work. The first one being the EV energy consumption modeling, then the human modeling for EV heating and cooling load, and the photovoltaic energy production modeling. Then I will discuss a case study and results, and then with conclusions and future work. So starting with the introduction, EV consumption modeling can be used to predict EV driving range for different drive cycles and environments. This can help reduce range anxiety by providing drivers with accurate range estimates. It can be used to optimize design for reduced energy usage or design better management algorithms and thermal management systems, and also design HVAC systems for energy efficiency while maintaining occupant comfort. In this work, we were also looking at vehicle integrated photovoltaics, which may be used to provide additional energy in electric vehicles for extending the driving range, reducing the frequency of charging, and powering secondary electronic systems. And there's been a growing number of projects integrating solar panels into vehicles, with some examples shown in the pictures here. When one is designing these VAPV systems, we want to know the amount of energy yield that we will expect to get from the solar panels in different geographic locations and different seasons. And if we're interested in using the VAPVs for charging the main EV battery, we also want to know how much range that additional PV energy can provide. So to do that, we developed this approach. And to describe the methods, I'll first start with a high-level overview and then discuss each component in more detail. So we coupled a thermal electrical PV model with our Titern 3D heat transfer software, where we made a vehicle cabin model. Then in the vehicle model, we use a human thermal comfort model to predict the necessary HVAC load that keeps the occupants of the car comfortable. So that gives us a consumed HVAC power time series. Also, we use the PV model and Titan vehicle model to calculate the amount of PV that's generated over time. Then we take these time series as inputs combined with some parameters about the electric vehicle and weather data, and use a zero-dimensional EV power consumption model to calculate the power consumption of the EV and how much of that consumption could be offset by having onboard solar panels. So going into more detail, first discussing the human modeling for the EV HVAC load. Many of the historical thermoregulation models are based on treating the human as a set of cylinders. And the thermal analytics, we've developed a human thermal model that uses more layers and elements than these historical models. And it's been validated with human subject and sweating mannequin tests. and allows for local sensation and comfort predictions. So our Titrum human thermal model consists of 20 body segments with layers representing tissues such as the bone, muscle, fat, and skin. And note that while we're using 20 segments to calculate the physiological behavior in the model, there can be multiple geometrical elements within each body segment to provide a high-resolution thermal solution. So the model is solving the bioheat transfer equation that is shown here, where this equation consists of the thermal diffusion equation with the effects of metabolism, environment, and blood perfusion considered through these imposed heat rate terms on the right-hand side. And these terms can be varying significantly over time, depending on the human's thermoregulatory state. The metabolic heat term is considering the temperature effects on the metabolism, heat due to shivering, and due to physical activity. The environmental term considers sensible and latent heat exchange with the environment. And the blood perfusion term is describing the heat transfer due to blood perfusion, where the values of the coefficients in front are determined from empirical models that were developed by Fiala and Whistler. Also, with this model, differences in physiology can be accounted for, like gender, height, weight, and body fat. And activity level is given as an input in terms of a met rate, or this stands for metabolic equivalent of task. And then other activities can be related to this met rate, like shown in the chart here. Also, different body sizes can be chosen in terms of the population percentiles. When modeling a human, we also want to model the clothing. This can be done using the clothing material database that is integrated into Titrum, or users can create and add their own clothing materials and specify the clothing properties, which include the thermal and evaporative resistance of the clothing, local clothing area factor to take into account the additional surface area on the body due to clothing, heat capacity, lateral conductivity, and the impact of liquid dependence on clothing properties. The HTM allows to predict the skin, tissue, blood, and core temperatures of the body, as well as the sweat rate, with the ability to specify custom sweat maps, and the shivering and vasomotion of the body. And then finally, these physiological predictions can be used to predict subjective thermal sensation and comfort, where sensation is describing how hot or cold something is perceived to feel, and comfort describes whether the sensation makes the person feel good or bad. We have several comfort metrics available in Titrum, and one of those is the UC Berkeley sensation comfort scales, which are shown on this slide. So an example of using the human thermal model for modeling HVAC is shown here. Here we are using an HVAC control algorithm based on human comfort. In the cool down scenario, where the cabin temperature starts hot and the HVAC turns on, it cools off, and then the HVAC power is reduced until the temperature stabilizes. So we see the Berkeley sensation also starts hot and reduces down to near neutral for the occupants. And then we can use that to also look at the cooling power consumption during that scenario. So here we were comparing the power consumption if the vehicle windows were made out of some standard automotive glass versus solar reflective glass. And next, I will describe the methods we use for photovoltaic modeling. of the vehicle integrated solar panels on the car. To predict the amount of PV yield, we need a PV system model, and there are many aspects to this which are nicely summarized in this figure. We need to consider the available solar irradiance and weather, then translate that irradiance to the irradiance that actually reaches the panels. While we're doing that, we need to account for reductions in the light that reaches the panels due to shading and soiling. And then we also need to consider the cell temperature, since that can significantly affect the module power output. And from there, we can calculate the module power. There are also losses related to the inversion of power from DC to AC and wiring and various things like that. In the work I'm describing today, we're mostly focused on the first 5 steps of the modeling in this chart. So why is it important to consider PV temperatures? It is because solar cell efficiency typically decreases with increase in temperature, and the performance of solar cells is often rated at 25 Celsius, while cells in operation reach significantly higher temperatures. So if we want an accurate energy production prediction, we should be considering the real operating cell temperatures. And as an example, as part of a study that we published a few years ago, we looked at the PV performance impacted by temperature and angle of incidence. So here, the blue curve is if we just look at the amount of irradiance that reaches the solar panels. Then if we include the losses due to the sun's angle of incidence on the solar panels, we get the orange curve, where we see some losses in the morning and the late afternoon when the sun is not at a perpendicular angle to the solar panel surface, which were horizontal in this case. And if we add the temperature impact, we see a larger impact on efficiency, especially in the middle of the day with this dip where the solar temperatures are the highest. We saw in the study that the performance of the system would be overestimated by 16% if these effects were not included. So by using a heat transfer solver for PV modeling, we can improve the accuracy of temperature and thus performance predictions for solar modules, especially if they are integrated into structures where it is more difficult to use simple empirical temperature approximations. It also allows users to analyze the impact of the PVs on the temperature of the structures, such as the temperature of the cabin, and they can be used for design of PV cooling techniques. So to do that, we use a coupled thermal electrical approach, where for the electrical model, we use an equivalent circuit model to represent the PV's electrical behavior. And from this equivalent circuit, we can write a nonlinear implicit equation for the current. Solving this will tell us the current versus voltage behavior of the device, from where we can calculate the generated power. And we couple this electrical model with time term at the time step level. And how that is done is shown in this flowchart. So at the end of each time step, we are retrieving the PV module temperature. If using the equivalent circuit approach, we then recompute the equivalent circuit parameters, which are all temperature dependent. And from there, we generate the current versus voltage curve, which describes the behavior of the PV panels. Then we find the power that is being produced, and then correct that power and efficiency for angular losses due to different angles of the incident solar radiation and any soiling losses. And then we apply a negative imposed heat rate that's equal to the power produced by the module to take into account the portion of the solar energy that's converted into electricity instead of heat, and write results to a file. There is also an option to use a simpler approach where the user specifies an efficiency and a temperature correction and calculate the power from there. So this coupled thermal electrical model is inside of the PV modeling extension prototype, which allows to quickly set up thermal electrical PV models with Titrum. This also includes the GUI shown here and a PV equivalent circuit parameter derivation tool that allows to derive the equivalent circuit parameters that are needed for the modeling from parameters that are readily available on manufacturers' data sheets. And with this extension, users can model factors that are impacting PV performance, like temperature, solar angle of incidence, PV soiling, and PV system level losses. And this prototype is available for evaluation if you are interested. So finally, the third aspect of this modeling is the EV energy consumption. For this, we are using a zero-dimensional EV model that is considering all of the main components of the EV, like shown in this diagram. And this is from an open source Python package that we adapted. So we have, as an example, here's a Titan vehicle model with PVs integrated into the roof and hood of the SUV. And we have a driver in the car where the HVAC load is calculated based on human comfort. Then Titan will consider the environmental effects on the system, such as the solar loading, radiation exchange with the sky, and wind convection, by applying boundary conditions that are specified in a weather file. Here we use the typical meteorology year data from NREL's National Solar Radiation Database. And then for the EV power model, we need a few inputs. We need the drive cycle, which are just the speed versus time series. So here are two examples, a city driving scenario and a highway drive cycle. We need the weather data. Then the HVAC load and the PV power are coming from the Titan 3D vehicle model. And we need to specify some electric vehicle parameters, like shown in this chart. Then running the EV model, it computes the overall power load time series for the EV, as well as the power loads and losses from individual components of the EV. And here are examples of the model output for the overall power load for the drive cycles. The positive loads here are consumption, and negative loads in this plot are due to power generated from regenerative braking. So now we'll describe the case study that we did using all of these methods. For our case study, we modeled the EV energy balance over 1 day for 2 drive cycles in each of 4 seasons in Phoenix, Arizona, and Detroit, Michigan, where the day consisted of a 40-minute morning commute, followed by 8 hours parked outside, and followed by a 40-minute afternoon commute. So the overall day is shown here. We have the 2 commutes, and then the park period where the vehicle speed is 0. And we did that for city and highway drive cycle. We used this model of the SUV with the PVs integrated into the roof and hood, and equivalent circuit parameters were derived from a PV module datasheet, looking at sun power, Maxian solar cells. For the steps in this work, to model a realistic scenario of the day using the car for commuting, we ran a series of Titan models. First, we have this house model where we find the garage temperature at the start of the commute based on the weather overnight, assuming that the car is parked in the garage. And then we assume that the vehicle is starting in thermal equilibrium with the garage. So we find the steady state temperatures of the vehicles. Then we transient restart that into a 40-minute commute, where now we have the driver in the car, and now we are calculating the HVAC load based on the driver's thermal comfort. To model the HVAC, we are using a fluid network in Titherm with specified airflow speeds. That fluid network is shown here, and we got the airflow speeds on the different parts of the body from CFD modeling of the airflow from the vents. Then we transient restart into a parked car model. So here we removed the human from the car and assume that the car is parked in an unshaded area for 8 hours. And finally, we transient restart into the 40-minute afternoon commute, again adding the driver back in and regulating the HVAC based on the driver's thermal comfort. So from all of this, we get a time series of the HVAC power loss and the PV power generation. For thermal comfort in this work, we used the predicted mean vote metric, which is a comfort metric developed by Feiner and standardized with an ISO standard. This is predicting the mean value of votes of large groups of people on a 7-point thermal sensation scale, ranging from -3 being cold and +3 being hot. And it considers the human activity level, Kelvin resistance, air temperature, mean radiant temperature, air velocity, and relative humidity for this metric. And this is also an output of the human thermal model. So we implemented this control algorithm, and the control is based on the value of the PMV and the rate of change of the PMV over time. So here's an example of a cool down scenario with this control algorithm. So the sensation is starting at hot, and when the AC is turned on, the sensation quickly drops. Then once it reaches near neutral, we start ramping down the AC in order to avoid overcooling the driver. And on this plot on the right are just the air temperatures in the cabin. So we see that the air temperatures in the front where the driver is reach reasonable levels of around 22 Celsius. In order to automate all of these Titherm runs, we used CoFirm, which is our coupling and process automation software. This has multiple applications. In this case, we're using it to automate multiple Titherm runs and couple with user-written Python code. But this can also be used to couple different CAE programs, like coupling Titherm with CFD, or performance sensitivity analysis, design of experiments, optimization, and surrogate modeling. So now I will show some of the results from this study. Here are the results of looking at the energy load on the EV and energy generation by the PVs in Phoenix, Arizona. So looking at the PV energy generation, we see that during commuting, amount of energy generated is very small. And this is mainly due to only a relatively short time spent commuting, and the commute occurring during the morning and late afternoon when the angle of solar irradiance isn't optimal for PV power generation. However, during the 8 hours that the car spends parked, the vehicle integrated PVs are expected to generate 10 to 23% of the total energy consumption for the city driving cycle and 3 to 8% for the highway drive cycle. It's a lower percentage for highway driving, simply because the highway driving is requiring more energy with the higher speeds, and also there's very little regenerative braking occurring. Then the table at the bottom is showing how this energy yield translates into range extension. And so we can see that the range extension could be 10 to 12 kilometers in the summer and around 4 to 5 kilometers in the winter. And here are the results for Detroit, Michigan. We notice there's more HVAC power use in Detroit in the winter due to the colder temperature, as could be expected. The PV energy generation is actually quite similar to Phoenix. One might think that there will be much less energy produced in Detroit since it's much further north, but the solar panels in Phoenix suffer losses due to the high temperatures in the summer especially, so there's not as much of an energy generation benefit as we might expect if we just looked at the solar irradiance alone. So in Detroit, we predict that the VAPVs would generate 5 to 19% of the energy consumption for the city drive cycle and 2 to 7% for the highway drive cycle. And that translates to 8 to 10 kilometers in the summer and quite low, only about 2 kilometers in the winter. We can also look at the impact of the VAPVs on the HVAC load, where we saw that the HVAC load was significantly reduced in cool-down scenarios due to the VAPVs converting some of the solar radiation to electricity instead of heat. So we see that in July for both Phoenix and Detroit, 5 to 12% decreases in HVAC load, and also in April for Phoenix, which was also a cool-down scenario. So seeing that we weren't getting that huge amount of driving range from the PVs when they are on the roof and hood, we looked at the impact of increasing the VAPV coverage. So we looked at putting VAPVs on all of the body panels and also adding even more transparent PV films onto the windows. And we saw that that does significantly increase the coverage amount to over double of what it would be if we just had it on the roof and hood. So looking at, we can also then look at VAPV power by vehicle part and look at some of the effects. So in Phoenix, with the horizontal vehicle parts like the hood and roof, it is just this parabola, which is the same shape as the global horizontal irradiance on the horizontal surface on Earth. But when we look at the sides of the car, then we have two local maxima in the morning and afternoon, because that is where the sun is shining more directly on the sides of the car. Then looking at the Detroit plots per vehicle part, here immediately was kind of interesting to see this big dip at around noon. And if you look at the cloud cover, we see that what happened here is there was a lot of cloud cover during that part of the day, and that really significantly dropped the PV energy production. And we saw a smaller dip here later in the afternoon, again, due to cloud cover. So it shows how sensitive PV systems can be to things like cloud cover. And so we can do this type of studies and try to optimize the placement of the PVs for the maximum power production. So for conclusions, we have demonstrated how a tighter model can be coupled with PV and EV models to calculate EV energy consumption with consideration of VAPVs and HVAC loads. For a full-size SUV with, in this case, it's a boxy SUV, so there was non-optimized aerodynamics. The amount of range extension expected from integrating conventional solar cells into the roof and hood was 2 to 11 kilometers per day, depending on the location and season. And we saw that a VAPV system that would integrate PV panels into all body panels of the EV could generate 2 to 2.5 times the yield of a system where you only have PVs on the roof and hood. We also saw that the VAPVs can reduce the HVAC load in hot conditions by converting a portion of the incident solar radiation into electricity instead of heat. And I just want to mention some ongoing and future work. We are currently working on a high-resolution EV model with a thermal electrical model of the battery pack, also explicitly modeling the cooling system. So some images from that model in progress are shown here. And with this model, we will be developing examples that study factors impacting the driving range and also the battery lifetime. So looking at the impact of the HVAC system, the battery cooling, environmental conditions, driving patterns, etc. This slide just has some references for more information. You can, of course, go to our website for general information. And here's a list of papers we published on the Titern PV modeling approach, and another few papers about the Titern human thermal model. So thank you for your attention, and I'm happy to answer any questions.
All right, thanks, Timothy. First question, in the energy consumption model, is it possible to consider the effects of wind convection and the different directions a vehicle is facing while it's driving?
Yes, so in Titern, there is an option under the natural environment modeling setup where you can specify the vehicle heading, and it can be a curve over time, so different directions based on some route that you can plan out. And you can also specify the vehicle speed from the drive cycle. So then the Titern model will consider the effects of the sun being from different directions and the wind convection of the car.
All right, thank you. Is it possible to consider the optical properties of the individual PV layers within the PV panels?
Yes, and I have a slide here describing that a little bit more. So we have a transparent material modeling solver in Titern, and this can be used for not just PV panels, but any type of automotive glass or other glass that is made up of multiple layers. So users can specify the individual layer thermal properties, and then also the transmittance and reflectance of each layer as a band average value or a spectral curve in Titern. If it's a spectral curve, the curves will be band averaged by Titern based on the solar spectrum. And then Titern will consider the individual reflections and transmissions through each layer of the transparent material to calculate the optical behavior.
All right, thank you. Did you consider the impact of the additional weight of the PV cells for the EV with the VIPV's case?
Yes, we did. I didn't mention it here, but one of the inputs for the EV consumption model is weight of the car. And when we modeled the car with VAPVs, we added some weight, an estimate based on the density of typical PV panels and the surface area coverage.
All right, well, looks like that's it for questions. So thank you, Timothy, and we appreciate everyone for attending today. You will all receive a follow-up email this afternoon containing links to download the presentation slides and watch the recorded webinar session. Again, thanks, Timothy, and everyone have a nice day.